Hello everyone, welcome to the 8th lecture of the series on AI using Python. In this lecture, we will discuss about activation functions in neural network. As we have seen in the previous lecture, a neural network or NN is a network of neurons which are arranged in layers. A neural network can be considered as a series of layers where each layer transforms its input data and gives some output, and the output of each layer will be the input of the next layer. Therefore, from a mathematical point of view, neural network can be considered as a composite function of the form as in this equation, where f0 up to fl plus 1 are the layers of the neural network, which are composite functions of the form sigma of ax plus b. So here f0 we call as the input layer, f1 up to fl are called as the hidden layers, fl plus 1 is called as the output layer. Now each of these functions has two components. The first one is an affine function, which is the linear component and it is of the form of ax plus b. And the second one is the activation function, which is the nonlinear component, and we can have different choices for the activation function. One of the popular activation function is the ReLU or the rectified linear unit function, which is basically defined by maximum of 0, x, where x is the input variable. So the ReLU function gives the output as 0 if the input is negative, and the output will be same as the input if the input is positive. Now this figure is a schematic representation of a neural network, which we have already seen in the previous lecture. Here, each of these red circle denotes a neuron, and a collection of neurons that takes the same input forms a layer. Here, this set of neurons forms a layer, which is basically the first hidden layer, and we can denote this mathematically by the function f1. And similarly, we have L number of hidden layers, and there will be one input layer as shown here, which takes the input data, and there will be one output layer which produces the output data. Next, we can try to have a better understanding of neurons and layers. Neurons, which are also called as perceptrons, are the building blocks of a neural network. And we can mathematically represent a neuron as a composite function as in this equation, where y is the output of the neurons and x will be the input of the neuron. In general, the input to the neuron or x can be a scalar or it can be a vector, which means we can have more than one input variables. And the output of the neuron or y will be a scalar. This means the neuron can be considered as a scalar valued function or a real valued function. And here x1 up to xn can be considered as the input variables. A1, A2 up to AN can be considered as the weights. This will be the elements of the matrix A. Now here we sum all these weighted input values and we add the bias B, which gives Ax plus B as the output. Now this activation function or sigma takes this Ax plus B as the input and it gives the output of the neuron. Here we can use different notations for x and y based on the location of the neuron. For example, if the neuron is in the first hidden layer, the input to the neuron will be x and the output of the neuron we can call as y11, y12 and so on. Now a layer is a collection of neurons that takes the same inputs. In a neural network, the neurons are arranged in layers, and in general, the layers can be grouped into three categories, which are input layer, hidden layer, and output layer. And in the input layer, each neuron has only one input, and it simply passes the input. So in the case of an input layer, we have the weight A will be equal to 1, and the bias B will be equal to 0, and the activation function sigma will be a linear function with the gain 1. So we have sigma of Ax plus B will be equal to x. Now, in the case of hidden layer, each neuron can have more than one inputs and it gives a scalar output. And the activation function in the hidden layer will be usually nonlinear. For example, we can select either ReLU function or tanh function, etc. Now, in the case of output layer, each neuron can have more than one inputs and it gives a scalar output. And in the case of output layer, the activation function is normally linear in the case of regression problem. However, when it comes to classification problems, we normally use nonlinear activation functions such as step function, sigma function, sigmoid function, etc. Next, we can move on to the activation functions. And in general, activation functions are the nonlinear component in a neural network. Now here we have a list of commonly used activation functions in a neural network, which are linear function, which is mostly used in the output layer only, and the ReLU activation function, which we have already seen in the previous lecture. And we have parametric ReLU function, which is basically a modification of the ReLU function, in which if x is greater than 0, the output is same as the input, and if x is less than 0, the output is equal to a times x. So here a is a parameter which is chosen as greater than 0. A special case of parametric ReLU function is called as the leaky ReLU function, in which the parameter a is chosen as 0.01. Now we have modulus function, for which the output is equal to the absolute value of input. Here this modulus function can be considered as implementing the full wave rectifier, whereas the ReLU function implements the half wave rectifier. Now we have step function, for which the output is equal to 0 if the input is negative, and the output is equal to 1 if the input is positive. In the case of step function, we can have only two possible outputs, which are 0 and 1. Now we have signal function, for which the output is equal to -1 if the input is negative, and the output is equal to +1 if the input is positive. We have the saturation function, for which the output is equal to -1 if the input is less than or equal to -1, and the output will be same as the input if the input is between -1 and +1, and the output will be equal to +1 if the input is greater than or equal to +1. Then we have the sigmoid function, for which the output is equal to 1 by 1 plus e raised to minus x. In the case of sigmoid function, the output will be within the range of 0 and 1. Another recently introduced activation function is the swish function, for which the output is equal to x into sigmoid of beta x. So this will be equal to x by 1 plus e raised to minus beta x. And then we can have tan h or hyperbolic tan function, for which the output will be defined as in this equation. Next, we can move on to the illustration of these activation functions in Python and compare their outputs. In the illustration, we will be considering a neural network as shown in this figure. So here we are considering one hidden layer, and the hidden layer will be having 100 neurons. And the weights and biases for each neuron are selected as random numbers. Now this M1 stands for the number of neurons in the first hidden layer, and here we are selecting it as 100. And the input data X is defined as 100 equally spaced data points between -10 and 10. And the output of the first hidden layer we denote it as Y1, and the output of the neural network we denote as Y. Now A1 contains the weights for the neurons in the first hidden layer. And here we are defining A1 as an array containing 100 elements, where each element is defined as a random variable. And similarly, B1 will be an array containing 100 elements, which has the bias values. And here also each element can have random values. Now for each element in the input array X or X of I, we compute the value of the Y or Y of I. And here the Y of I is defined as sum of the elements in the array Y1, or in other words, sum of the outputs of each neurons in the first hidden layer. Here Y1 of j stands for output of the jth neuron in the first hidden layer. And here this output will be defined as ReLU of Ax plus B, where A and B for each neuron will be different. And it comes from this random array A1 and B1. Now we can plot X versus Y, which gives a plot as shown in this figure. Here we can see that if we are rerunning this simulation, we get a different plot. This is because of the reason that every time we rerun this code, the weights and biases will be different. So it will give us a different output. However, one important observation is that here the output will be always positive. This is because of the reason that here we are using a ReLU activation function, and the output of each neuron in this case can either be 0 or it will be a positive value. And we define the output of the neural network as sum of the output of each neuron. So that's why we got large positive values here. So this is equivalent to have an output weighting matrix or A2 as shown here, which is a matrix containing 100 ones, and the bias B is equal to 0. Now to get negative outputs, one possible way is to introduce negative values in the output weight A2. And this we will be illustrating next, in which the output weight A2 is chosen as a random array of size 100. So here we are using the same input, and A1 and B1 are chosen as random array of size 100. And here we define A2 as a random array with 100 elements, and B2 will be the bias for the output layer, which will be a random variable. Now, as before, the output of the neurons in the first hidden layer, or y1 of j, is defined as ReLU of ax plus b, where a and b comes from the array a1 and b1. Then the output of the neural network, or y of I, is defined as a2 into y1 plus b2. So here the output will be weighted sum of the neurons in this first hidden layer, where the weights comes from the array a2. Now we can plot x versus y in this case, which gives the plot as shown in this here. Here we can see that the output can take negative values as well. And here, if we rerun the code, we can get both positive and negative output values depending on the elements in the weight matrix A2. Next, we repeat the example with other activation functions and see the possibilities. First, let's consider the modulus activation function, and we can plot the graph of the modulus activation function using this code, in which we are using the absolute function from the NB library for computing the modulus function. And for each input value in the array X, the output Y of I is defined as absolute value of X of I. It will basically give the magnitude of the input as the output. Now we can plot x versus y, which gives the output of the modulus function as shown in this figure. So where we can see that the output will be always positive. Next, we can consider a neural network with one hidden layer, which has 100 neurons with the modulus activation functions. Here we are using the same input as in the case of ReLU illustration, and the only difference is that the output of the neurons in the first hidden layer, or y1 of j, is defined as absolute value of ax plus b, where a and b comes from a1 and b1. Now we can plot x versus y, which gives the output as shown in this figure. And here also, if we rerun the simulation, we can get different outputs. And based on the random values chosen in the weights and biases, the shape of the output varies. And another observation is that here also the output will be a piecewise linear function, as in the case of ReLU function. And this is because the modulus function is a piecewise linear function. However, since we have selected large number of neurons in the first hidden layer, this may look like a smooth function. But if we zoom it out, it is actually a piecewise linear function. Next, we can move on to the step function, and first we plot the graph of the step function, in which we use the Heaviside function from the NP library. And here this 0 specifies the output of the step function if the input is equal to 0. Now we can plot x versus y, which gives the graph of the step function as shown in this figure. So here we can see that the output is equal to 0 if the input is negative, and the output will be equal to 1 if the input is positive. And the function has a discontinuous jump at the input equal to 0. Next, we can consider a neural network with one hidden layer, which has 100 neurons with a step activation function. And here the code is similar as in the previous case. And the only difference is the output of the neurons in the first hidden layer is defined as step of ax plus b, where a and b comes from a1 and b1. Now we can plot x versus y, which gives the output as shown in this figure. So here also we can see that the output is piecewise linear. This is because of the reason that step function is a piecewise linear function. However, here we can observe is that the folds are more sharp as compared to ReLU function. This is because of the discontinuous nature of the step function. Now here also, if we rerun the simulation, we can get different plots. And the output can be either positive or negative based on the weights and biases. Next, we can move on to the signal function. And here we will be using the sine function from the NB library. And it basically gives the output as -1 if the input is negative, and the output as +1 if the input is positive. Now we can plot x versus y, which gives the output as shown in this figure. Now we can consider a neural network with one hidden layer that has 100 neurons with the signum activation function. And here the output of the neurons in the first hidden layer are defined as signum of a1x plus b1. Now we can plot x versus y, which gives the output as shown in this figure. So here also the output is piecewise linear, and we can see that the folds are sharp as in the case of step activation function. And this is also because of the discontinuity or the infinite slope of the signal function at 0. And here also we can rerun the code for getting different plots. Now we can move on to the saturation function. And for plotting the graph of the saturation function, we will be using the clip function from the NB library, where in the clip function we can give the lower bound and upper bound of the limiting values in the saturation function. Here we are giving the lower bound as -1 and the upper bound as +1. So the output will be a saturated output within the range of -1 and +1. Now we can plot x versus y, which gives the output as shown in this figure, where we can see that the output is within the range of -1 and +1. And if the input is less than -1, the output will be saturated at -1. And if the input is greater than +1, the output is saturated as +1. Next, we can consider a neural network with the saturation activation function. And here we are defining the output of the neurons in the first hidden layer as saturation of A1x plus B1 with the limits -1 and +1. Now we can plot x versus y, which gives the output as shown in this figure. And we can rerun this code for getting different outputs. Here also the output is piecewise linear, but we can see that the output is more smoother as compared to the signum or step functions. Next, we can move on to the sigmoid function, where we implement the sigmoid function as 1 by 1 plus e raised to minus x. And we can plot x versus y, which gives the output as shown in this figure. So here we can see that the output is in the range of 0 and 1. And for sigmoid function, we have a smooth curve. Now let's consider a neural network with the sigmoid activation function. And here the output of the neurons in the first hidden layer are defined as sigmoid of A1x plus B1. Then we can plot x versus y, which gives the output of the neural network as shown in this figure, where we can see that the output is a smooth curve, and this is because of the continuous and differentiable nature of the sigmoid function. And here we can rerun this code and get different plots. We can see that every time we are getting a smooth curve. Now let's move on to the switch function. And for plotting the graph, we are defining output y of I as x of I divided by 1 plus e raised to minus beta x of I. And here the value of beta is chosen as 0.5. Now we can plot x versus y, which gives the output of the switch function as shown in this figure. And we can see that switch is more like a continuous approximation of the ReLU function. Now let's consider a neural network with the switch activation function. And here the output of the neurons of the first hidden layer are defined as A1x plus B1 divided by 1 plus e raised to minus beta A1x plus B1. And then we can plot x versus y, which gives the output shown in this figure. And here we can see that the output is a continuous and smooth curve. And by rerunning this code, every time we are getting a smooth curve. Finally, we can move on to the tanh function. And for plotting the graph, we are using the tanh function from the NB library. And the output y of I is defined as tanh of x of I. Then we can plot x versus y, which gives the plot as shown in this figure. And here we can see that the output will be in the range of -1 and +1. Now we can consider a neural network with the tanh activation function. And here the output of the neurons of the first hidden layer will be defined as tanh of A1x plus B1. And we can plot x versus y, which gives the output as shown in this figure. And here also we obtained a continuous and smooth curve. And by rerunning this code, we can see that the output will be always a smooth curve. Now we can move on to the comparison of different activation function. And first we can plot the graph of each activation function together. And here we will be comparing the output of 8 different activation function. And the output values we defined as ya up to yh. So here ya is defined using the ReLU function. Yb is defined using the modulus function. Yc as the step function. Yd as the signal function. Ye as the saturation function. Yf as the sigmoid function. yg as the switch function, and yh as the tanh function. Now we plot each of these output versus x. We obtain the plot as shown in this figure. Here we can see that the graph of the ReLU function and switch function are somewhat similar. For this function, the range of the output values is also similar. And also for the positive values, the output of the ReLU and modulus function are also similar. And the range of output for the modulus function is also same as the ReLU and switch function. And similarly, we can see that the step function and signal function has similar plots. And the output range of step function is from 0 to 1, and the output range of signal function is from -1 to +1. And we can see that the graph of the sigmoid, saturation, and tanh function are somewhat similar. The tanh and saturation function has the same output range, which is from -1 to +1. And for sigmoid function, the output range is from 0 to 1. Now we can compare the output of a neural network with these different activation functions. And as before, we are considering a neural network with one hidden layer and 100 neurons in the hidden layer. And the weights and biases for the neurons are chosen as randomly. And it comes from the array A1 and B1. And here also the outputs are corresponding to the different activation functions such as ReLU, modulus, step, signum, saturation, sigmoid, switch, and tanh. Now we can plot the input versus output for each of these activation functions. And the plot will be as shown in this figure. Here we can observe that the output of the ReLU function and switch function are somewhat similar, where the switch function gives a smooth curve and the ReLU function gives a piecewise linear curve. And similarly, the output of the saturation and tanh function are somewhat similar, and the output range is also similar, which we can observe here. And the sigmoid function also has a similar output, whereas the range is slightly different. And finally, the step and signal function gives somewhat similar outputs, which we can observe from here. However, the ranges are different. And the reason behind this behavior is the similarities between these various activation functions, which we have seen earlier. Here we can rerun this simulation, and the similarities can be observed every time we rerun the code. So in these simulations, we have selected the weights randomly and plotted the output. Here what we have done is selected some random weights and biases and computed the output data. Now in the case of training, we have to do the reverse process. In other words, we will be given with the input and output data, and using which we have to find the weights and biases for a specific neural network structure. In that case, we will be deciding which activation function we are going to use in the neural network. And based on these plots, we can say that if we are using tanh or saturation activation functions, the values of the weights obtained for a given data will be approximately the same. Similarly, for ReLU and switch activation function, the weights and biases will be somewhat similar. This we can observe when we are training a neural network with different activation functions and looking at their weights and biases. In the next lecture, we will be discussing how we can use this neural network for solving regression problems. With that, we comes to the end of this lecture, and thank you.